Welcome to Navakokon Education Society's Divize College online session conducted by Shriram Dandekar. We have studied the theorem on inverse functions derivatives. The most important part in 12th standard for inverse functions is inverse trigonometric functions, and today we will see some derivatives of inverse trigonometric functions and some solved problems in the book. The first theorem of the inverse trigonometric functions is the derivative of sine inverse x. Now in this we must know what is the domain and codomain, what is the inverse function, etc. In 11th standard we have studied the trigonometric functions. Observe here sine function. For the sine function, domain is set of real numbers, range is closed interval -1 to +1. This function is not 1 and onto function that we have seen. Look at this graph. In this graph, x can take any value from negative infinity to positive infinity. If we draw any line horizontal to or parallel to the x-axis, we can see that this line intersects in infinitely many points to this graph. Therefore, this function is not 1 function. This function is 1 only for this part, from -π/2 to +π/2. If I take any horizontal line, then it will intersect only in one point, and therefore it is 1 function. Also it is onto function because from -1 to +1 all values are attended between -π/2 to +π/2. Therefore this function is 1 and onto. Now why I am telling this 1 and onto is that only because the function is 1 and onto, then only it is invertible, and therefore for this domain closed interval -π/2 to +π/2 towards closed interval -1 to +1, the function sine is invertible and its inverse exists, and that inverse is defined by sine inverse x is equal to theta if sine theta is equal to x, where x belongs to closed interval -1 to +1 and theta belongs to closed interval -π/2 to +π/2. Only in this case the inverse of trigonometric function sine exists. In section 1 we have to study these inverse functions. This is what there in section 1 we must know. For this sine inverse, domain is closed interval -1 to +1 and the range is from -π/2 to +π/2. Similarly, for cos inverse function, the domain is closed interval -1 +1 and range is closed interval 0π. For tan inverse function, domain is set of real numbers and range is open interval -π/2 to +π/2. remember that tan pi by 2 not defined. Therefore, tan inverse something cannot be pi by 2. That something is finite, I am assuming. Cosec inverse R. The domain is set of real numbers minus open interval minus 1 to plus 1. This is because the values of sine theta are from minus 1 to plus 1. Therefore, cosec theta cannot take values from minus 1 to plus 1 being reciprocal of sine theta, and therefore other than these minus 1 to plus 1 all real numbers is the domain for cosec inverse function. That means if someone asks you what is cosec inverse 0, then tell them it is not in the domain and its range is closed interval minus pi by 2 to plus pi by 2 except 0. Then sec inverse theta, its inverse also exists for the domain set of real numbers minus open interval minus 1 to plus 1 towards the range 0 to pi minus singleton pi by 2. Now again move to our discussion towards the derivative of inverse functions. Inverse sine function. This sine function, in sine inverse function, its domain is closed interval minus 1 to plus 1 as we have seen. That means x can take values from minus 1 to plus 1, and the value of sine inverse, that is y, it is between minus pi by 2 to plus pi by 2 including them. Then the derivative of this sine inverse x function is 1 upon under root 1 minus x square for mod x less than 1. Now what is mod x less than 1? Mod x less than 1 means minus 1 is less than x is less than 1. But here minus 1 is less than equal to x is less than equal to 1. Mod x less than 1, that is x between minus 1 and plus 1. This is because x square is in the denominator, under root 1 minus x square, the term is here. If this term becomes 0, then this dy by dx is 1 upon 0 and it is not defined in mathematics. Also in the theorem of inverse function we have studied that dy by dx is equal to 1 upon dx by dy provided that denominator dx by dy is non-zero. Therefore this condition is there and we have removed this equality and taken strictly less than. Now let us see the proof. Given that y is equal to sine inverse x, minus 1 is less equal to x less equal to 1 and y is between minus pi by 2 to plus pi by 2. Remember that only under these conditions we can invert the function and we can find its inverse x is equal to sine y. This inverse is due to these restrictions on x and on y. Let us differentiate this x with respect to y. Dx by dy is equal to derivative of sine y with respect to y. Derivative of sine y with respect to y is cos y. But cos y is square root of cos square y. I don't know whether it is positive or negative, therefore I have initially given positive or negative square root of cos square y. Now we know the fundamental identity in trigonometry, cos square y is 1 minus sin square y. Therefore this dx by dy becomes plus or minus under root 1 minus sin square y. Again sin y means x. Sin y means x, putting it here I get dx by dy. Sin y is equal to x. Putting here we get dx by dy is plus or minus under root 1 minus x square. But cos y is positive since y lies in first or fourth quadrant. First or fourth quadrant. First quadrant from 0 to pi by 2 and fourth quadrant from minus pi by 2 to 0. Therefore, in first and fourth quadrant cos y positive because the derivative is cos y positive. Therefore, I am taking this dx by dy as positive square root of 1 minus x square. So, dx by dy is positive square root of 1 minus x square. Now, by theorem that we studied of inverse function, dy by dx is equal to 1 upon dx by dy, and therefore dy by dx is equal to 1 upon under root 1 minus x square. Here we have to take the precaution that the denominator should not be 0, and denominator is non-zero only when mod x is less than 1. Therefore, we have proved dy by dx is equal to 1 upon under root 1 minus x square for mod x less than 1 when y is equal to sine inverse x. This is the proof of the first formula. Derivative of sine inverse x is 1 upon under root 1 minus x square. The second trigonometric functions for its inverse derivative, there is cos inverse x. Now for this cos inverse x, the domain is same -1 to +1, but the range is from 0 to pi. For sin theta it is from minus pi by 2 to plus pi by 2, but for cos the range is 0 to pi, and then its derivative is dy by dx is -1 upon under root 1 minus x square. The proof is very easy, exactly on the same lines. This thing as it is except this y, this line as it is differentiate with respect to y. Dx by dy is derivative of cos y with respect to y. Now derivative of cos y is minus sin y, and so there is change, and using that changes we can prove that dy by dx is equal to -1 upon under root 1 minus x. The third one we are going to study is y is equal to cot inverse x, its derivative. For this the domain is x belonging to the set of real numbers, and y the range is from 0 to pi. Then its derivative dy by dx is -1 upon 1 plus x square. Since x belonging to r and 0 to pi is the limits for y, the function y equal to cot inverse x is invertible, and for this invertible function I can write x is equal to cot y. X is equal to cot y. Differentiating this with respect to y, derivative of cot y is minus cosec square y, but using the fundamental identity in trigonometry, this cos square y can be replaced by 1 plus cot square y. Again this cot y is nothing but x, so it becomes dx by dy is equal to -1 upon 1 plus x square. We have dy by dx is equal to 1 upon dx by dy by theorem that we have studied, and therefore dy by dx is equal to 1 upon -1 plus x square, that is dy by dx is equal to -1 upon 1 plus x square. The proof of y equal to tan inverse x, its derivative is 1 upon 1 plus x square. This is very easy, just like cot inverse x. In place of this cot inverse x, we take tan inverse x. The domain is x belonging to R, and range is between minus pi by 2 to plus pi by 2. This is not the range of tan inverse. This range is for cot inverse. For tan inverse, the range is minus pi by 2 to plus pi by 2. Then x is equal to tan y. Differentiating, we get sec square y. Sec square y is 1 plus tan square y. So it is 1 plus x square. Then inverting, we get the answer dy by dx is equal to 1 upon 1 plus x square. You can solve this, and if you cannot, then please ask me on my mobile phone. The next inverse trigonometric function, for its derivative is y equal to sec inverse x. The domain for sec inverse x is mod x greater than equal to 1, and its range is 0 to pi except pi by 2. For this, the derivative dy by dx is 1 upon x under root x square minus 1 for mod x greater than 1, for x greater than 1, and it is equal to minus 1 upon x under root x square minus 1 for x less than minus 1. Before entering to proof of this, let me tell you one thing. Look at this graph. For this graph, this part is not correctly drawn, because for sec inverse x, its value should never be between minus 1 and plus 1. Here the value between minus 1 and plus 1, this graph portion is not drawn correctly. What you have to draw is like this. For pi, sec pi, the value is minus 1, and it goes like this, and this never intersects the line x equal to pi by 2. Just like this curve is here, you should draw the curve like this. Please correct your textbook with this graph. Now let us move to the proof. Y sec inverse x. For this domain and for this range, the function is invertible. So after inversion, we get x is equal to sec y. Differentiate it with respect to y, we get derivative of sec y as sec y into tan y. But tan y is under root tan square y, that is under root sec square y minus 1, that is x under root x square minus 1 we get. Certainly it is plus or minus. Let us discuss about their signs. The value of y is in either first quadrant or in second quadrant, and therefore sec y into tan y is always positive. That means x into under root x square is always positive. Either x is greater than 1 or x is less than minus 1. In both the cases, sec y into tan y should be positive. Remember that this term under root x square minus 1, we are taking it positive always. And therefore, if sec y, that is x is negative, then applying negative to a negative number gives me a positive number. Therefore, for x less than minus 1, we have taken negative x into under root x square minus 1. But for x greater than 1, I have taken positive value x into under root x square minus 1. And therefore, in first and second both the quadrant, we get a positive value. And therefore, the derivative dy by dx is 1 upon x under root x square minus 1 for x greater than 1, and dy by dx is minus 1 upon x under root x square minus 1 for x less than 1. The proof ends here. Next one is derivative of y equal to cosec inverse x. The proof is exactly similar. The difference is when derivative of sec inverse is positive, the derivative of cosec inverse is negative, and vice versa. When derivative of sec inverse is negative, derivative of cosec inverse is positive. All the terms are same. All these results are summarized in this table given in your book, table 1.2.1. Derivative of sine inverse x is 1 upon under root 1 minus x square for mod x less than 1. Derivative of cos inverse x, tan inverse x, cot inverse x, sec inverse x and cosec inverse x. This table you must remember. We can apply the chain rule in the derivative of inverse trigonometric functions. We know that derivative of sine inverse x is plus 1 upon under root 1 minus x square. So derivative of sine inverse fx is f dash x upon under root 1 minus fx square for mod fx less than 1. Or we can say that derivative of sine inverse bracket is derivative of bracket divided by under root 1 minus bracket square. Similarly, the remaining derivatives you should go through. For example, derivative of cot inverse bracket is minus derivative of bracket divided by 1 plus bracket square. To solve the problems on derivatives on inverse functions, you must remember some formulae that are there in your first section. First one is sine inverse sine theta is equal to theta and sine of sine inverse x is equal to x. This is just f and f inverse. When they come together, you get identity function. For all the 6 trigonometric functions, these formulae are there. Cos inverse cos theta is theta, cos of cos inverse x is x, tan inverse tan theta is theta, and tan of tan inverse x is x, and so on. Whenever for derivative, if there comes something like this, sine inverse of cos theta, remember that in 10th standard you have studied cos theta, sin theta, cot theta, tan theta, cosec theta. They are the allied angles for sine of pi by 2 minus theta, cos of pi by 2 minus theta, etc. So cos theta is replaced by sin pi by 2 minus theta, or sin theta is replaced by cos of pi by 2 minus theta, tan theta is replaced by cot of pi by 2 minus theta whenever required. All the 6 are like this. Now we know that sin x is 1 upon cosec x. So that is only for remembering this formula or these 6 formulae. Sine is inverse of cosec, therefore sine inverse x is cosec inverse 1 by x. Cosec inverse x is sine inverse 1 by x. Take just reciprocal. Similarly, remember the pair cos and sec. Cos inverse x is sec inverse 1 by x and sec inverse x is cos inverse 1 by x. Remember the next pair tan and cot. Tan inverse x is cot inverse 1 upon x and cot inverse x is tan inverse 1 by x. Also remember these 3 identities. Sin inverse theta plus cos inverse theta is equal to pi by 2. tan inverse x plus cot inverse x is pi by 2, sec inverse x plus cosec inverse x is pi by 2. In the section 1 we are also going to prove this. Tan inverse x plus tan inverse y is equal to tan inverse x plus y upon 1 minus xy, and similarly tan inverse x minus tan inverse y is equal to tan inverse x minus y upon 1 plus xy. Few more formulae are there, but we are going to take them while solving problem only. In this session it is enough. Thank you.